last lecture, the main things we talked about were two main theorems. One I call the residue theorem. Very easy to prove, but nevertheless. And one I call the degree theorem. Let's try to remember these theorems. We begin with a remark. Namely that if you have a meromorphic function and it has a pole, say at 0, for example, so you have the principal part of it plus homomorphic terms, say at 0, for example, it doesn't matter. And quite often you write this thing, well, the degree of this pole is well defined, but these numbers are really dependent on the coordinates. So the remark is that the numbers a minus n and so on depend on the coordinate of choice. That's the bad news, but if we have, say in this case, 0, and we take a circle around 0, gamma, and we write omega equals the meromorphic function dz, so a one form, then this integral of this meromorphic one form, omega around gamma, is equal to a minus 1, independent of the coordinate, independent of the choice of coordinate. So what this leads us to understand is that the right objects, the correct object, here in this context, is not a meromorphic function, is a meromorphic one form. And of course, Riemann knew that. I mean, the great mathematicians of the past understood that very well. So we have to define that. So the definition of a meromorphic one form is a definition of a meromorphic one form. It's very simple, of course. It's a one form. So let X be a Riemann surface. So I'm emphasizing here that it's an abstract thing. You could think of something, domain in the complex plane, but we should think abstractly, it's a Riemann surface. And let's say pk, this is going to be the points where this form is going to have poles. So pk is a discrete set. In x, so x is some mysterious thing. It could even be just a plane domain, which is just fine. Let me draw it as perhaps mysterious. Let's say a pair of pants. Here's a pair of pants. I don't know. Maybe it's even more interesting than a pair of pants. This pair of pants has a pair of pants or something. Something like that. I don't know. It doesn't matter. Right now, it doesn't matter. And in this case, it has boundaries, so, well, it could accumulate to the boundary, P1, P2, and so on, Pn, some discrete set. And now you a meromorphic one form on X. A meromorphic one form on X. With poles, let's say, at the pKs. Is one, two things. It's a holomorphic one form, on, if you take out the poles, you take out all of the poles, and it's a holomorphic one form. So let's remember what that really means. It means that in local coordinates, it doesn't matter which local coordinate you choose. Say z, but not at a pole now. Omega of z, and now let's just say a general thing is going to, as you know, it's going to be f of z dz plus g of z dz bar. I just wrote down for you a completely general one form. Right? And now with two conditions, g is identically 0. Okay. So and that condition is a well-defined condition for holomorphic coordinates. So this is identically 0. So that means that omega is nothing more than just f dz. And that's the kind of thing we have all the time, f dz in coordinates, right? That's what we integrate all the time here in complex analysis. And just to emphasize, this is we call this a 1-0 form. So that means 1-0, you have this thing here, but none of this thing here. So that's a 1-0 form. And 2, f is holomorphic. That's the thing that we've talked about forever in complex analysis. It's a holomorphic form, but it's holomorphic outside the poles. 2, so at a pole, at a pole, say with coordinate I don't know, let's have another coordinate, w, omega is equal to m of w dw, so it's a 1-0 form, but m of w near this thing is a pole, so let me just write it, w minus w at a pole, say p minus w of p, to whatever order it is here, so this is n, and to whatever the order here of n is at p. So if you write it down, and maybe even better, this should be a pole, so this should be negative. So this is 1 over w minus w at p, some number, to some n, I don't know, some n here, times the unit w. Well, I didn't write the unit here, unit of w. That's the way the meromorphic function should look. And that's the way it is. Is that okay? locally it's just a meromorphic function times dz. Okay, so that's what is a meromorphic one form. Okay. And now if we have a domain D, which is say an open set in a Riemann surface, and it has decent boundary, you know, if you don't have decent boundary, it can be horrible. Right? It's just something, it can be really horrible. The boundary of something can be really horrible. So we assume with piecewise smooth boundaries that we can apply Stokes' theorem. So I don't mind having a few singularities of the boundary. So this is D sitting inside some Riemann surface. And thanks. This is D sitting inside some Riemann surface. Now there's a little warning about these things. If you have I think there's an example that was suggested for some other purpose by Nicolas. If you take, say, for example, a torus, and there's some problems here. For example, you say, well, we have a smooth curve. That's a smooth curve. But what is it bound? There's some problem here what it bounds. I mean, if you cut this Riemann surface here and take it apart, it's a cylinder and you have two curves. Right? So there's some, yes. So when I say that really it bounds something, I mean it bounds a region in the usual sense. So that is not allowed here. It doesn't bound anything. So right now I won't allow that. So what I want to allow, this is good here. D could lie over here like this. That's allowed, of course. It bounds something. There's some problem with what it means to bind to it. Okay, so when you have this thing, so you can forget the Cauchy integral theorem completely. Just the only theorem around this place is Stokes' theorem, as you know. And if you have a meromorphic one form, so omega is a meromorphic one form. And the first thing you do if you're doing any kind of calculus at all, you look at d omega, d omega, and this is equal locally to equal to d of m dz. And this is equal, I'm going to do this out long and really slow and just brutally. This is equal to the partial derivative of m with respect to z dz plus the partial derivative of m with respect to z bar dz bar dz bar. That's how you take d of something, the derivative dz, the derivative of the bar dz bar, wedge dz. And dz wedge dz is 0, and then let's turn this around here. This is minus, to get this thing right, you have to, I like to have dz first for some unknown reason. Probably it doesn't matter, some unknown, I have no idea why. That. And this thing is meromorphic, but it's holomorphic outside some points, and this is identical to 0. Cauchy Riemann equations. Okay, so you see that the integral, the general formula of the Cauchy integral theorem, which is Stokes' theorem, is the integral around the boundary of D, which, since it's piecewise reasonable, you could do the Stokes' theorem of omega is the integral over D of d omega, which is 0. If you know Stokes' theorem and you believe everything you're dealing okay, smooth and so on, then there's nothing going on here, it's just that. Okay. So that's pretty interesting. Well, wait a minute. What do we do here? We change from the boundary to the whole domain. And here's D, and if that's a smooth form, Stokes' theorem says that we can do this. Right? Stokes' theorem says that we can do this. But this form is only meromorphic. Stokes' theorem says this is okay for omega holomorphic, so no poles, but otherwise it's not okay, right? Because there are some poles in this guy. So let's assume these poles can't accumulate, it's not allowed. So they have poles at these points. So you might have some poles outside, so I don't know, poles, P1, P2, and so on. So we do the usual thing and put little circles around the thing. So I recommend the notation d epsilon is equal to d minus the disjoint union of disks, coordinate disks of radius epsilon about the poles. Yeah. Now, it only makes sense in coordinates, but I mean, it doesn't matter, as you know, it doesn't matter at all by writing coordinates, whatever. Now I'm okay, that's now okay. Namely, the integral around the boundary of d epsilon of this meromorphic form. This is holomorphic on d epsilon now. But the boundary has become big, is 0. And the boundary is the integral around d. And now the trouble is that I put either these disks in here, and this is we have those boundaries here because the orientation is the opposite, so we have a minus around these disks of omega, and that's equal to 0, and so that says that the residue theorem is new theorem. I'm still reviewing what I said yesterday, but it doesn't hurt. The residue theorem then says the integral around d of, and let's scale it now so that we can get really the right numbers, around d of omega equals the sum of the residues at the poles of omega. Right? And now, if you wish, you can write in coordinates, say at pk, you know what it is. So we just wrote it someplace on the blackboard. I'll write again, omega is some meromorphic function with some, you don't know what these darn things mean. But you have the principal part of this guy, and then you get this a minus 1 term where you have the pole of order 1, and that's what you pick up. So that's the sum of these things, the sum of the a minus 1s at the pKs. Okay. Those are the residues. And it's a wonderful thing, as I mentioned yesterday, you localize the integral at these polar points. It's a great way to compute this integral. This integral might be horrible, but computing these things is a joke. If you know, I mean, it's just you just write the thing down and get it. So that's interesting, and the formulation that I write here is I'm even going to sum over P in D of the residue at P of omega, because what I'm now going to define the residue at a place where it's holomorphic is there's no residue. So I'm only adding up finitely many terms. And this is a beautiful statement of the residue theorem. Okay? Well, let's just for fun, take an example of something like this, just for fun. Let X be a compact, whatever that is. Today we're going to have many examples. A compact Riemann surface. Then let's let an omega be a meromorphic one form on X. Now, X is compact. So we're really lucky here, we don't have to worry about infinitely many poles or something like that, because they can't accumulate, right? So let's just make a note, only finitely many polar points, only finitely many polar points. So you don't know where they are, and that might really make a difference. But what you say is, okay, what the heck, I'm going to draw a picture, let's say maybe it's compact now, so it looks like something like here. Has two holes. Just as a sort of warming up to the notation, we say here the genus of this thing is the number of holes, and that's G. So this is a Riemann surface of genus G, which in this case is 2, with 2 holes. Okay. We'll talk about that, what a classification is of these things as a differentiable manifold. And we'll talk about that in a little bit. But right now, just a picture, just whatever that means, 2 holes. And then you have a certain number of poles, P1, I don't know, so really number of poles, whatever. P2, maybe P3 over here, I don't know, whatever. And now you do the same thing, only, in fact, no outer boundary, so I take disks around here. Yeah. So I take X minus the disks, the union of the small of the disks. These are the disks d epsilon at pi, at the pi. My teacher, I used to love it. My teacher of complex analysis was a German, and he had a heavy German accent, and he would talk about, you bore out the holes around on the points. He was a wonderful man. He left Germany as a, you know, if you leave Germany, he was a Jew who was pushed out of Germany, of course, had to go to Israel and so on. But he left it as an adult, so, you know, if you learn a language when you're an adult, you don't lose the accent. You're lucky people. So when these Germans here, they learned the language when they were kids or in school, so you have no accent. Right? That's nice. So you bore out the hole. Yes? And let's call this D. This is D. It's okay, it's allowed. It bounds the rest. I just told you. And in the rest, there are no poles. Right? No more poles in the rest. This is D. So this is D. So the integral around the boundary of D, the way I just wrote it down there, of omega, so D is the rest, you see, it's after the whole. So that's just the number, that's the sum of the residues over D of omega, and there aren't any, that's 0. Right? Okay. But that says that the sum of the residues on this side is 0. Right? Because the integral around the outside bound, I'm looking, there's 2 sides of life. you know? Right? There's, if you start with, you look at the outside, this is D here. And you can regard, of course, this is orientation, which way you go around, but the outside here is D, and its boundary is the boundary of these circles, is the boundary of these discs. Or you can just take the union of these discs, and that's also, you can apply that, right? So this is also, by the way, this is the sum of the residues P in X of omega. Inside or outside, right? It doesn't matter. It's an incredible theorem. It's an incredible restriction on a meromorphic one form on a compact Riemann surface. The sum of the residues is 0, punct. You ought to smell something, that smells really amazing, doesn't it? You just write blah, 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 and then the sum of the residues of a meromorphic one form on a Riemann surface is 0. I'm sorry, so let me just write this theorem up here. So the theorem is just Stokes' theorem. If omega is a meromorphic one form, so in this sense, compact Riemann surfaces are great. One form on a compact Riemann surface as X, then the residue of omega, which is the sum of the residues of P in X, of the residues of omega is 0. Something. Right. Okay, so that's a very interesting thing. That's the residue theorem. And that's everything about residues. Now let's go to the degree theorem.
So,
yeah.
isn't that the residue around the poles is A minus 1?
That's right.
Why it's 0 in this?
Hmm?
I didn't get why it's 0 in this.
Yeah, let me say it again. So I'm going to use his language now. So you have a meromorphic one form. And at each of these points, you have A minus 1 at each of these points in some coordinates, right, of this meromorphic one form. And you're going to add up these A minus 1s all over these points, and the answer you're going to get is 0. Isn't that amazing? But the reason is that the integral around these boundaries is either the integral of the boundary of the outside or either the integral of the boundary of the inside. Well, of course, there's a sign change. But if it's 0, it doesn't matter. And if you integrate over the outside thing, there are no poles, so there are no residues. It's 0. That's the reason it's 0. So there are no poles outside. If you do the inside, you get a pole each time. So you get the residue each time. You add them up, you get 0. Isn't that amazing? Yeah. Anytime you see a whole number, like 1 or 17 or something, or even 0, it becomes interesting. So this degree theorem, there's a little bit of preparation that you should do for yourself. Is if you have a meromorphic function, say a meromorphic function on X, on anything, say X, then you can try something exciting by taking the log of it. Okay? Now please remember that the logarithm is the inverse mapping of the exponential map. If you took e to the m, it would be all right maybe. Well, as a pole, I don't know what e to the infinity is and all that. This is dangerous. Right? But the log of it is not well defined. Right? Because there are many logs. Yeah, okay, so that's not well defined. Not well defined. Now let me make a historical remark. This didn't bother Riemann in the slightest. Right? Riemann didn't worry about functions that are not well defined, that are multiple values, like this. He didn't care. And the reason is he was really thinking about holomorphic forms, or meromorphic form. Riemann didn't care. So some function like this is locally holomorphic, and no particular choice of what we call a branch of the logarithm. You have many possible definitions. That didn't bother Riemann at all. Many possible definitions. But the reason it didn't bother Riemann was that what Riemann was going to do is take d of this guy. Okay. Now let's think about that for a minute. Remember the inverse. You remember the inverse of log. The inverse of log. The difference is well, here's the exponential mapping, and on the kernel of the exponential mapping, all these things are the difference of 2 pi I. So the inverse is just if you take one choice, the other choice differs just by some multiple of 2 pi I, right? Okay. So Riemann says, well, hey man, we have here m a choice. I have to write it down here. Log of m at choice 1. Sorry here. I have to write it. Now I know what I'm doing. Log 1 of m of z minus log 2 of m of z. Yeah. Riemann knew. We have to write it down because we have to be formal. Right? You have two choices. Log 1 and log 2. This is just some multiple. I don't know what the multiple is. It's 2 pi I times k. Right? Some multiple of the choice, right? Because of, right? It's the periodicity of the exponential maps the other way around, right? It's the inverse map. Exponential map is, well, and then when you're having fun, if you take d of this, that's d of a constant, and that's 0. So it says if you take d of this thing, it doesn't matter. Okay? Right? So it says that d, so given a meromorphic function on x, then you have a meromorphic one form, d log n. That's a notation, really, because the different values of log, but it's what it is. Okay? Now, you're not surprised to know in coordinates so m, say, equals to m of z, then d log m, I mean, you learned this even from me in Mickey Mouse mathematics, is m prime over m dz, right? Right, that's how you take the derivative of the logarithm, right? So that's what it is in coordinates, right? Well, that's very interesting. Let's look at that. Let's look at that. So let's suppose m in local coordinates, in some local coordinates, let's suppose that any local coordinates, I don't care. M is z at some point times the order of m at that point. So if the order is positive, nothing's going to happen here. We're not going to get anything. And then locally, then well, we just what it is m prime over. So d log m. Well, you can help me here. Let's see if I'm any good. So the order comes out, and then we have log d of z minus z of p plus d log of the unit. Did I do that right? Right, log of something times something is log of something plus the log of something, right? And so I just took the log of this stuff, and then the exponent comes into the front. And so it's here, I put it in the front, and it's this, 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 this. And of course, then the integral of d around a small disk, so let's say here's p, and then here's a circle around this p, here's the point p, so that's gamma. And then, so let's scale this integral so we understand what's going on. So we integrate d log n around this gamma, and of course, this thing is really defined. So this is really just u prime over u, locally. And so let me write it all down now, so you get the order, I'll bring it out in front because that's a number, so I'm going to even write it carefully. This is the order of the meromorphic function at p times 1 over 2 pi I integral around gamma of d of that thing. Well, we know what that is. That's the key thing in life for complex analysis. Cauchy integral formula, I mean Cauchy kernel z, plus the something here, 1 over 2 pi I, same thing, I'm going to write it here, u prime over u, dz. And now what is this? What is this? This thing is 0 because this thing is holomorphic. And this thing is here 1. So this whole thing is just the order of the pole of p. The order of m at p. Yeah?
So d ln m should be, so you need a multiple of om on the other d as well.
I do.
Yes.
Well, I thought, let me just make sure. You mean here?
Yes.
Well, let's see, I don't know, log of z minus zp, I'll just write O times u.
Oh, never mind, you don't actually. You don't.
You don't,
Yes, you don't, it's okay.
so, it's an exception, I didn't make a mistake.
It's okay.
Okay, so you agree, it's okay. So anyway, this thing's holomorphic because u is a unit, it doesn't contribute anything. And you get the contribution here from the Cauchy integral, and so you get the order. This order could be positive or negative. Right? I don't care. It's just the order. It could be vanishing. Or, yeah? Okay. So it says if we have, again, the situation of D contained in a Riemann surface, and you have then, and here's D, and here's the boundary of D, piecewise smooth or smooth. And you don't want to integrate through a pole, that's what we were just joking about last time. So you assume, I mean, you don't want to have some, so we assume that the divisor, so M is meromorphic in the neighborhood, so I write to be precise on the closure of D. That means it's some neighborhood, and divisor of D, M, that's where it has zeros and poles. Let's say the support of this thing is finite, of course, and it does not intersect the boundary of D, so I'm worried about integrating through a pole. So the divisor is where it has zeros or poles, you don't know. Okay? So you have all these places around here, you have some pole like I had up there, P, and at each point P where I have a polar of a zero, I have the order here, because that's, if this thing is the number 2, that means it has a 0 of order 2 there. If this thing's order minus 17, it has a pole of order minus 17 there. Right? Well, it says now, if you have that set up, it says that if m is meromorphic here, then the integral, the integral 1 over 2 pi I times the integral, this makes sense, log n, d log m over the boundary of d. It's just the residue theorem again. It's the residues inside, I wrote down what the residues are. There they are. Well, it's the degree of the divisor of m. Right, and where you're going to ask something, Nicholas, what?
So is it then just the degree of the divisor at P? Suppose that we only have one.
No, I mean, you have a bunch of these residues. I mean, this is at P1 you have, and then you have at P2, you have something here at P2 and so on. You have,
So they are compact, or
huh?
do we also say that the subset is compact?
So, well, thank you very much. So I assume that, yeah, okay, so, yeah. So the boundary should be piecewise smooth compact, so, and bound this domain. So otherwise it's a horrible thing. You're right, I should say that.
And then degree of the divisor is then the sum of all the degrees.
Yeah, so in general you might have infinitely many zeros, infinitely many poles, but since this thing is compact, that's your point. Yeah, so what you're saying, you have all these things, but of course this is compact and I wrote here very carefully, look at this, I even was careful. The support of the divisor, that's where it's either a zero or pole, doesn't intersect the boundary. So we were talking about this last time, so you don't have to worry about integrating through something that's singular. Okay? So that's the total degree of the divisor, and this is the sum for P and D. In this case, finite. Well, otherwise we can't do this really. For P and D of the O M and P. And it's the same thing. You can write this the sum of P and D of the degree of the divisor of M at P. Okay. That's what the order is. Well, that's the degree formula. It's the same thing that we had before, and now the same proof as before. Exactly the same proof as before, theorem. This is the degree theorem for X compact. It's the same theorem. So you have a meromorphic function on a Riemann surface. Let me just remind you, we might have a lot of compact things here going on. This is genus genus 5. 5 holes, right? So you have and you have a meromorphic guy on this Riemann surface. That's going to be the whole thing. Remember, problems, particularly problems 2 and problem 3, are questions about meromorphic functions on a Riemann compact Riemann surface. So now that you have the support of the divisor at various points, the support of the divisor is finite because this thing is, that's Nicholas's remark. It better be finite because the thing's compact. And so that's no problem. And so there says that the degree of the divisor of the meromorphic function is 0. Right? Because it's the same thing I just argued over here. Is the integral inside or outside? You pay your money, you take your choice. Inside you get the degree of the divisor. Outside you get 0 because there's no contribution. Right? I'll draw the picture again. You pull out the disc. We will bore out the discs. I really love Max Schiffer. He's wonderful. So we bore out the discs, And you have inside and outside. If you think of this as being the boundary of the outside, you get 0. The boundary of the inside, you get the degree of the divisor. This is an amazing thing, right? So it says, there are very strong restrictions to meromorphic functions on Riemann surfaces, yes.
Where does it fail when you have non-compactness or non-compact?
Well,
surfaces?
yeah, it's a good question, because inside, if inside, and that's what I talked about, inside is bounds the domain, this say bounds the domain.
Mm-hmm.
Right, but if outside is non-compact, you can't apply Stokes.
Oh, okay. And that's why because we integrate over the boundary of the whole manifold surface.
Yeah, if you have a compact thing and you have a curve like that, that really bounds 2 places, right? Okay?
Okay, yeah, I see.
Okay, this is very beautiful, I think. The degree theorem and residue theorem, particularly for compact Riemann surfaces, because it's a very strong statement. And now, in the remaining time in the first lecture today, I would like to start with examples, okay, of compact Riemann surfaces. Okay. So, I remind you of Remmer's theorem for non-compact surfaces. Shows you have many holomorphic functions. You might even look at this. So Remmer tells us that for X non-compact, you have many holomorphic functions just by restrictions. There's a mapping, not canonical, of course. Then X can be realized in C3 and maybe even C2. So a closed complex submanifold. So many holomorphic functions come from restriction. Now you don't have any, so if X is compact, then of course you don't have any non-constant holomorphic functions. So you're not going to embed it in C3. You're not going to embed it in some vector space. You're not, right? Because any place you have restriction of holomorphic functions, it's not going to work out. Right? So the Italians, which I've told you is part of my mathematical heritage. In fact, even in beginning geometry in the education in university, they talk about X in projective space. And analogous to Riemann into what I call 3-dimensional projective space. Italians, when they do geometry, they do what we call projective geometry. And you will learn what that means. But in particular, you see, Remmer gets this in C3 and gets many holomorphic functions on X. And the Italians realized that a Riemann surface is embedded in P3, and that you get many meromorphic functions from P3. So it's here, holomorphic functions by restriction, holo by restriction, or pull back, depending how you want to write it, and here meromorphic functions by restriction. Now here it makes a difference. Many Riemann surfaces do not go into P2. This is a dimension of the manifold. 3 is dimension. So dimension of Pn of C, whatever that is, it's an n-dimensional manifold. And so in this case it's 3. Okay. Now, the first, I would say, big remark is given X, compact, it is, in my mind, difficult to prove that there is even one meromorphic function that is non-constant. And it's the same thing on non-compact. It's difficult to prove that there's even one holomorphic function that's non-constant. This is the non-trivial thing. This is the difference between calculus on manifolds, which you're learning, some of you are learning here, right? It's trivial to construct smooth functions. And the reason is you have partition unity. You can piece things together with partition unity, right? But because of the identity principle, just think partition unity all the time. Here it's 0 almost everywhere and so on. Here's a function which is 0 here on an open set. It certainly is not holomorphic, because if it's 0 on an open set, it's 0. Right? The identity principle is really a huge obstruction to construction of functions. So these results of this type, that you can really embed this thing here and so on, are very deep things. And that is one of the goals that I have, is proving that. Okay. So for the remainder of the lecture, and probably some more this afternoon, I'm going to talk about construction of projective space. Okay. So what in the devil does that mean? What is this thing? Okay. Okay. So the beginning point you begin with the simplest thing that you can think of is a complex vector space. V equal a complex vector space. Now, this complex vector space, there are very important vector spaces that are infinite dimensional. Namely, for me, those spaces are function spaces. Spaces of functions, right? And for other people, there are other things, but for me, the function spaces are these horrible, well, not horrible, they're wonderful, but this thing should be finite dimensional. Complex space of finite dimension. And now, when you're just staring at this space, at this thing, so you've had some experience with linear algebra. When you look at a complex vector space, You say, what could possibly be associated with that? So you look at interesting subsets. Now, if you're doing linear algebra, if you're doing analysis, you might look at some open subsets and integrals and various things, but if you're doing linear algebra, you're looking at linear subsets. So here we're going to do the first thing. So let's say linear. And that, by that we mean W, let's say W, a subspace. Linear. And this is, you might have some idea about a picture. Here's 0, and here's some linear subspace. Well, it's not compact, it goes out to infinity, but you think of that might be W. It's hard to draw because it's highly non-compact, right? So linear subspace. And of course, you see that's by the by a mega problem for infinite dimensional spaces because some linear subspaces are closed, but it's a big theorem if you can prove that a linear subspace. We talked about this yesterday. For the image of Fredholm operator, the image is a closed subspace. That's really a serious thing. So this will be in fact closed. In particular, it's a subvector space. And it's closed in the vector space topology. So it could not be more wonderful. Right? Now there was a high school teacher in Germany. This is quite obvious. Quite in the old days, in the 19th century, almost everybody thought all he could do is be a high school teacher, so he trained to do that. For example, Weierstrass. For example, all sorts of people. Hi. And a very interesting person who was completely autodidactic as far as I can understand. His name was Grassmann. I think he was in what is now regarded as the eastern part of Germany someplace. He was thinking on his own, and he studied vector spaces, although he didn't know the definition of vector space. But he tried all sorts of things. He even had the idea of you take what we would call a vector and then divide it by another vector. He had all sorts of fantastic ideas, many of them right. And so in some sense, the first part of this lecture is devoted to Grassmann. He lived alone, and I'm not sure, and he had all sorts of ideas in philosophy, and so I think he was just an amazing person, probably. Very early in mathematics, compared to the rest of the people. And what Grassmann said is, he said, you should consider the Grassmann set. Well, he didn't call it Grassmann. And by the way, some mathematicians are not so subtle. So there's a very important mathematician by the name of Stefan Banach from the great school of functional analysis in Lvov in the Ukraine. It's called Lviv maybe or something in Ukraine. And Stefan Banach's, every one of his Banach spaces is called B. Or denoted by B. Yes, you can look at his books. Well, Grassmann didn't call it this. In fact, he was so subtle, he just wrote things down. I mean, it was very hard to understand what he was talking about. So, this is a set of all W subspaces. So, subspace, not all subspaces of V, such that the dimension of W is K. okay? That's a set. Now, since all of you have had some experience in geometry, let me mention why that set is important. In geometry. It parameterizes all the k-dimensional subspaces. That's what it is. It's the parameter sub. It parameterizes all the k-dimensional subspaces. Let's think about this. You have this abstract nonsense with tangent vectors and tangent spaces and all of that stuff in manifolds. Well, suppose you have a manifold you learned something about manifolds. Suppose you have a submanifold N, a submanifold, let's just say of some big Rn. Right? You know the Whitney theorem, you can always embed a manifold, but it's not canonical. But quite often, your manifold, let's say your manifold is dimension k. This is some big Rn, right? Maybe you even want to take a 3-sphere in R4. Why not? But let's do it a little bit more abstractly. So you have something like this. This is M. It doesn't have a boundary, but I mean it's closed submanifold. And you have here at every point, as you know, you have at every point, this is point P, you have the tangent space of P at M. Right? And the most important thing, so if some guy or girl, usually girls are much smarter than guys, so they would never say the following stupid thing. But some guy says, following stupid thing, he says, well, what the heck do you care? You take over here a point Q, and these two tangent spaces, you think they're different, but any two vector spaces of the same dimension are equivalent, right? Well, they're isomorphic. Yes, but they're not the same. And to really understand what is the same, look at this. There's a map, M. It's called the Gauss map. From M into the Grossman map, it's a manifold actually. The Grossman, well in this case, it's maybe a real vector space. So it's the Grossman of Rn that takes a point P to the tangent space of P. Yeah? So as you move, it's called the Gauss map. As you move around, well, just have fun doing it on a sphere, on a 2-sphere. Yeah? You see, you have all of these, this is a 2-sphere, so all these planes are moving. As you move around the sphere, they're moving. Yes? So that means to every P, you have the tangent space of P, and this is in the Grossman manifold, it's a manifold, of K-planes in Rn. Yeah, that's the way to think of it. Okay? And the better way of thinking of it is this. Here is M. Here is Rn. Rn is the tangent space of Rn. Rn is the tangent space of Rn is the tangent space of Rn is the tangent space of Rn. Right? They're all the same. So at each point of P, I have Rn. Here's another point Q. I have Rn. I have all these. That means I have the tangent space of Rn at every point. All these points I have the Rn is Rn is Rn. Is Rn is Rn is Rn. Right? And now look, in Rn, so the whiteboard is Rn, you have the tangent space at P, and now it moves. And here you have the tangent space at Q. It's moving, and over here you have the tangent space at some other point, P, Q, R, I don't care. You see the picture? As you're moving along M, Rn doesn't change, but the tangent space inside of Rn is changing. You see it changing? Right? That's the picture you should have in your head. Okay? And Grossman had that picture in his head. And he knew, well, this is cotemporal with Gauss more or less. I don't know whether he read Gauss, and I think he closed himself in a closet most of his life. So I don't know what he knew. He was very creative just on his own. So that's the idea. These moving planes parameterized they give you a curve in the Grossman manifold. So this would give you a curve in the Grossman. Okay. Now here I'm interested in complex subspace. So a complex subspace. Okay. Okay. And we are going to consider, I will lecture for 5 more minutes and then we will eat. So, no, it's a good time to go eat now, I think, right? And then be back at 1 o'clock, right? You have more time. And let's, okay, can we go? Okay, so that's the next idea, to really understand Grossman's idea, and then move to projection space. Okay.